Hello. Today we'll explore a new feature in our software, iron losses in the machines. At the moment of creating this video, this feature is available for our permanent magnet synchronous machine components, while in the future we plan to include it for more machines. Instructions on how to use this feature will be shown in the example model created for this purpose, PMSM with iron losses. This example model can be found in the electrical drives example folder. This example model consists of two parts. The first one is the drive system with the PMSM and its control algorithm, and the second one implements the calculation of the iron losses and the machine temperature. Output of the iron losses calculation part of the model is sent to the PMSM machine, where it is included in machine state calculations in real time. First, let's explain how to enable this feature. If we enter properties of the PMSM, for nonlinear, spatial harmonic type, we'll see a checkbox at the bottom of the electrical property called iron losses. Enabling this checkbox creates an additional input on the machine, where you can provide the value of iron losses in watts. In the machine, we model the iron losses with a resistor, which is calculated based on the value provided to this input. This resistor then impacts the current centering the machine, which means that we have a more realistic model of the PMSM. A more comprehensive explanation on how iron losses impact the simulation can be found in the documentation for the permanent synchronous machine with salient rotor. The second part of this example model is the algorithm for calculating losses and machine temperature. In the first part, we calculate some of the losses of the machine, specifically eddy current losses, hysteresis losses, and stator winding losses. When we sum the values of the first two loss types, eddy current and hysteresis losses, we obtain the iron losses. This sum is then sent to the machine iron losses input, as we previously explained. The motor losses calculation takes several inputs: the speed of the motor and each of the machine currents in DQ domain. The value of the eddy current losses and hysteresis losses are calculated based on 2D lookup tables, which take the speed of the machine and the amplitude of the current vector. Stator winding losses are calculated based on the product of the current and the stator resistance. The second part is the subsystem, where the thermal calculation takes place. On top of the machine losses values, this subsystem also takes ambient temperature as a parameter. Based on the inputs, the machine thermal constant, and the machine thermal resistance, we can calculate the current machine temperature. Let's go to SCADA to see how this model functions in real time. In order to start the machine, we have to change the speed reference. When the machine reaches steady state, we can see instantaneous values for current power losses and the corresponding mechanical power output as well. However, since there is no mechanical load on the machine, these values are low. Now, when we increase the mechanical torque, it will highly impact the power losses values and the consumed power, which can be noticed in the widgets. In addition, changing the machine torque also increases the machine temperature, which can be seen on a temperature widget. This concludes a general overview of the iron losses calculation method in Typhoon Hill Control Center and the example model dedicated to it. Thank you for your attention.